An apparent solar day is related to the hours of daylight, and 12 noon is halfway between sunrise and sunset. In a peasant society, which does not use clocks and does not need to keep time to the minute, this type of day has been used for centuries, and still is in many parts of the world. But you cannot base any simple mechanical device on a day which changes in length over the year. So an apparent solar day does not meet the second of our requirements. It is not of constant length. The solution is to average out the solar day over a year. We take a particular point on the orbit. We define the time that it takes the Earth to return to that point as 1 year. The Earth rotates 365¼ times in that period. We therefore take the total time in a year and divide it by 365¼ to arrive at the length of an average day. Another word for average is mean. This is where the term Greenwich Mean Time comes from. This gives us what we call our civil day. It is a mean solar day. It is sometimes helpful to think of the Sun travelling westwards around the Earth, rather than the Earth spinning eastwards. In the case of mean time, we consider the mean Sun to be circling the Earth every 24 hours. This is the basis of local mean time, which we will discuss in a future lesson. Greenwich Mean Time has been used by mariners for centuries and is based on the rate of Earth rotation. However, we now know that over time the Earth's spin rate is actually slowing down slightly. The most accurate clocks available are based on the vibration rate of a cesium atom, and these are now used as the basis for international time. Therefore, Coordinated Universal Time has replaced GMT. The difference amounts to about half a second a year, so to us as aviators it has no practical effect. When required, a leap second is introduced to bring the two into line, but most people are never aware of it. We will use the terms Coordinated Universal Time, or UTC, instead of GMT from now on. The civil day meets our two basic requirements, of being related to daylight and of constant length. However, it does mean that 12 noon on our clock is not usually the exact moment of meridian transit. The difference can be as much as about a quarter of an hour over the year. This difference is called the equation of time. This is a graph of how the difference changes over the year. The vertical axis is UTC, and the red curve indicates the time of meridian transit. As you can see, there are only 4 days a year when 12 noon on the clock is exactly as the Sun crosses the meridian. The maximum difference is 16 minutes in November, when the real Sun crosses the Greenwich meridian at 11:44 UTC. The next biggest peak is in February, when the difference is 14 minutes, as the real Sun crosses the Greenwich meridian at 12:14 UTC. We also need to be able to define the length of a year. Again, there are several options. We could define with respect to a distant point in space. This gives us a sidereal year. A sidereal year is just over 365 days and 6 hours. However, the inclination of the Earth's axis changes by a very small amount year by year. To take account of this, and to have a year's length in phase with the recurrence of the seasons over the years, we need a very small adjustment. A tropical year keeps the seasons in phase. Its length is 365 days, 5 hours, 48 minutes and 45 seconds. But we cannot run a calendar and have a quarter of a day left over at the end of the year. The new year has to start with a new day at midnight, not 6 hours into January the 1st. Therefore, we have a calendar year of 365 days, except when it's 366. This explains why we have leap years. Suppose that this is the Earth's position in its orbit on the midnight ending the 28th of February one year. A year later, we are at the same calendar date at midnight, but the Earth is quarter of a day short of its previous position on the orbit. After 2 years, it will be 12 hours short. After 3 years, it will be 18 hours short. And after 4 years, it will be 1 day short of its previous position. We now add the 29th of February to the calendar, and the Earth catches up to its position of 4 years ago. The calendar is back in phase with the tropical year. If the difference between the calendar year and the tropical year were exactly 6 hours, that would be the end of the story. Unfortunately, it is 5 hours, 48 minutes and 45 seconds. Therefore, we need some fine adjustment. The normal rule is that if a year is divisible by 4, it is a leap year. So 2008 was a leap year, but 2009 was not. 2012 is, and so on. However, whole centuries, such as 1800 and 1900, are also divisible by 4. The first of our adjustments is that centuries are not leap years. This corrects most of the error, but there is still a tiny amount left. We need another adjustment. Every 4th century is a leap year. Thus, 1900 was not a leap year, but 2000 was. These rules may seem complicated, but you are required to know them. So let's try to put it simply. Every 4th year is a leap year, unless it's a century when it's not, unless it's a 4th century when it is. Let's summarize this lesson. You need to know about time because you should know why different countries keep different times, and how to find what the standard time is in any country you may land in. You also need to be able to work out when it gets dark in different parts of the world at different times of the year. In order to understand this, you need to know something about elementary astronomy. Kepler's first law is that the orbit of each planet is an ellipse with the Sun at one of the foci. There is a near point called perihelion, which occurs on or around the 4th of January. The actual date varies, depending on where we are in the cycle of the leap year. The far point is called aphelion, and occurs on or around the 3rd of July. Kepler's second law is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. Kepler's second law means that the length of an apparent solar day can vary between 23 3/4 hours to 24 1/4 hours over the year. A sidereal day would give us a constant length, but would not be related to day and night. The solution is the civil day, or mean solar day. However, using a civil day means that 12 noon on our clock is not usually the exact moment of meridian transit. The difference can be as much as about a quarter of an hour over the year. The difference is called the equation of time. The maximum difference is 16 minutes in November. The next biggest peak is in February, when the difference is 14 minutes. A sidereal year is just over 365 days and 6 hours. A tropical year keeps the seasons in phase. Its length is 365 days, 5 hours, 48 minutes and 45 seconds. A calendar year is 365 or 366 days. We use leap years to keep the calendar year in phase with the tropical year. The rules are that every 4th year is a leap year, unless it's a century when it's not, unless it's a 4th century when it is. That concludes this lesson on time. The next one will look at the Earth's tilt and the seasons.